Hi everyone, this is Mr. Campagna, High School for Medical Professions. I'm here to show you lab number 3, particle motion and phase change. So you have a couple things on here. You have your video tutorial that you probably scanned to get here, and you also have a link to the website that you need to use. So this is an online simulation using PhET's simulation tools. Very, very cool stuff here. So it's a little complicated. I'm going to walk you through it the best I can, and hopefully you'll be able to finish this lab independently. It says here, Part A, phase change. On the top right, notice the options to view neon, argon, oxygen, and water. Experiment with adjusting the amount of heat applied to the system using the control at the bottom of the container. Notice you can see the temperature change as you apply or remove heat. Head to the temperature converter to see how Kelvin unit compared to Celsius or Fahrenheit. You'll need to use a conversion later on. When ready, hit the reset all on the bottom right corner. They actually moved it on this. So it says here, complete the chart below by sketching the shape of the different substances while solid. Well, if we look here, we've got neon, argon, oxygen, and water. And neon, if you take a look at it, neon right now is in that crystal lattice shape where you got a whole bunch all close to each other. The attraction between them is definitely high, strong attraction. If I were to pull the attraction down, you'd see how they start to move apart. But in this case, it's definitely that they have a high attraction. So how would we draw this? Well, for neon, I would just start off by drawing a bunch of little circles that represent our atoms, all in rows. You're going to do the same thing for argon. These are a little larger, so you might make them a little bigger. But again, they're very close together. Oxygen, you can see oxygen are in pairs. So when you draw them in pairs. Oxygen likes to mate up with other oxygens if given a chance. That's how most of the oxygen in Earth's atmosphere is found in the form of O2. And then lastly, water vapor, right? You'll do the same thing with that. Now you'll notice that the water vapor is kind of bouncing around quite a bit, and those hydrogens, those little guys, right, because it's H2O, one oxygen and two hydrogens, those hydrogens tend to form hydrogen bonds between the atoms, and it starts to cause them to spread apart. So once you've finished drawing all these and do them completely, don't do what I did, we move on to question 3. What do you notice is different about the arrangement of water molecules in solid form compared to the arrangement of molecules in other substances? Well, if we look here, this is water in a solid form. If I heat it up, we could try and melt that water. We could try to melt that ice. And what happened to it? Definitely changed. So let's go back. I'm going to reset. This is what neon and argon and oxygen look like when they're solid. And this is what water looks like. Question B. Did you know water is the only substance on Earth where the solid form is less dense than its liquid form? Select the water option at the top and click between the solid and liquid phases. Using what you observe, explain why the solid form of water is able to float in the liquid form. So once again, here's our water in our solid form, frozen. But if we heat it up, we get it to be liquid. You can see that it definitely changes. And then if we cool it down again, you can start to see it expand. So explain why the solid form of water is able to float in its liquid form. If you need a hint, look close at the screen. That's not the whole answer, but maybe that'll give you a hint. 4, click between solid, liquid, and gas for each substance and pay careful attention to the attraction between the molecules in each phase. For each state, rank which has the greatest to least attraction. So let's go back, we'll reset, look at neon, and let's look at its interaction. It seems to have a very strong attraction to each other. Let's look at argon, maybe a little less. Let's look at oxygen, about the same. Let's take a look at water. So, if you now know that one that has high attraction looks like this, you know that the solid has high attraction. Let's add some heat. Let's turn it into a liquid. Okay, so we're in the liquid state now. So what gives? What happened to the attraction? Write it down. If we keep heating it up, what happens to the attraction? Write it down. Going to restart. Number 5, click Reset All on the bottom right. Select any of the 4 substances to place in the container. Increase the heat at the bottom of the container and observe. Can you tell when your substance changed state from a solid to a liquid? So take a look as I increase the heat. Something's happening just about there. It changed. What happened? The molecules are moving further apart. And we call this melting. I'd like you to do the same thing for liquid to gas, gas to liquid, and then liquid to solid. How do you get this liquid to turn to a gas? Just crank the heat up. Next, question number 6. What is happening to the volume and density of your selected substance as it is being heated? Good question. Volume is how much space it takes up, and density is how many particles are in the same area. Think about that. Answer it. Number 7. Click Reset again on the bottom right. Use the thermometer at the top to try and find the melting, boiling, condensation, and freezing points. So you can see here at the top we have a thermometer. That's 14 Kelvin, and that's negative 259 degrees Celsius. Now, those are the same. They're the same temperature, just different ways of writing it. So let's see what the melting point of neon is. So I'm going to select neon, and I'm going to increase the temperature until it melts. Seems to have melted just about there. Molecules are definitely moving apart from each other. I'm going to call that 26 Kelvin. Well, what is that in Celsius? It looks like it's negative 246 or 247. Now let's go to the boiling point. Let's make this thing boil. So we want to see the molecules move around, but not completely fill up the container. I might have went a little high. I mean, that looks pretty good, right about there. Let's call it at negative 244 degrees Celsius. And what would that be in Kelvin? 29 Kelvin. Next up is the condensation point. Condensation is when things start to drop out. So I've got all these neon molecules floating around, but I want them to come back down, so I'm going to cool it off a bit. And it looks like the condensation point is about there. Let's go with 12 Kelvin, which translates to negative 261. And lastly, our freezing point. Let's keep bringing down the temperature until everything forms a nice structure. I don't know if we're going to get much tighter than that. And that is negative 270. And in Kelvin, that is 4 Kelvin. So you're going to do the same thing for all those, for argon, oxygen, and water. And lastly, for 8, pick one of the 4 substances and graph the 2 phase changes as it's being heated, and a separate graph showing the phase change as it loses heat. Choose any units for time on the x-axis, that's the sideways axis, and use Celsius as your units on the y-axis, that's this one. label the phase change as well as the substance is a solid, a liquid, or a gas for both. So here's time. I'm just going to make up some units because we really aren't tracking time on this application, on this app simulation. So I'm just going to make up units. We can call them minutes, we can call them seconds. It really doesn't matter in this case. We're going to call it time. Let's call it seconds. And then as far as temperature is concerned, we're going to use degrees Celsius. Temperature in degrees Celsius. And now I got to figure out the range. Now, since I have neon here, I might as well use this. My lowest was 4, my highest was 29, it looks like. So basically I got to separate this into boxes so I can get up to 30. So in this case I would start off maybe with a 0, 5, 10, 15, 20, 25, 30. I think that works nicely. And I could start plotting out my points. So its melting point was at 26. So at 26 Celsius, and then the boiling point was 29. So, well, what would be the order of this? Well, we would probably start with the lower temperature and work our way up. So we'll start off with 26, which would be right about here. And we're going to continue it across until the halfway mark, because again, we said we're only doing the 2 transitions here. So this would be melting up until the 5. And then over here for the boiling point, it would be 29. So 29 would be right up there. So you're going to have a graph